Hello everyone, thank you for joining today. My name is Brenham and today we're going to be looking at gravitational potential. So we have a few learning objectives and that's to define what gravitational potential energy GPE from now on actually is. To understand the factors that change GPE, and to understand that gravitational potential energy in joules is mass in kilograms multiplied by G, which is gravitational field strength, kilogram, multiplied by height difference, which is in meters. Now, if you're ready, let's get right into it. Okay, so let's have a look at what gravitational potential energy actually is. Well, gravitational potential energy, or GPE for short, can be defined as the energy change associated with an object as it moves through a height. So now every time you hear, or see in a question, oh, a change in height, right, an object moves through X distance, right? Now you think, oh, that object either gains or loses gravitational potential energy. So if I go back to my figure 1 here of my ball of mass m being raised through height h, you can see that this ball is undergoing a height change, right? It is up here and it's going to fall down and it's going to end up down here, right? So it's going to move through a height h. So in this specific example, the ball is going to be losing gravitational potential energy as it's going from a higher height to a lower height. So think about it, right? At here, it has max. Let's say E. Remember, E for energy. Subscript just showing exactly what type of energy it is. So at that point there, at the top, right? Call that point A, right? It has the maximum amount of gravitational potential energy, and it has the, or rather 0 and 0 KE, right? It has 0 kinetic energy because it's staying still. But here, or just before it hits the ground, this has max. Now it has maximum kinetic energy and 0. Okay, so sometimes we can say that, oh, objects at the surface of the Earth have 0 gravitational potential energy. So physically, that's not really correct, but it's correct enough that we can use that to describe gravitational potential energy changes. Now you understand what gravitational potential energy actually is, right? It's always got to do with when an object through a height. Now let's have a look at its equation. So sometimes you might even just hear it be called just simply potential energy. Either way, it means the same thing. It is equal to m divided by g divided by h. Okay, so now let's have a look at all of our units. So again, n, as always, joules. Mass, again, standard unit, kilograms. Now, g, this is called the gravitational field strength. So this really describes strength of gravity around a certain object. Earth, a common value for this is 9.8 and it's used a newton per kilogram. But again, the keyword there is on Earth. On the moon, which is much smaller than the Earth, has a smaller mass and so it has a weaker gravitational field strength. It's about 1/6 of this, so it's around 1.4 like that, right? So you have to be very careful with this and read your question very thoroughly. Don't just think, oh, it's always 9.8. It can vary with planet. Then we also have our height difference, which is in meters and standard unit. Okay, so now let's have a look at the two factors that can affect gravitational potential energy, which is the mass. Well, actually, we have three features here rather: mass, gravitational field strength, and height. Because none of them are really sort of constant. Right? So if you have at a constant planet, right? So a constant gravitational field strength on Earth, the EGP. Now, for a constant mass on a constant planet, we can just cancel m and g out. So directly height. So if we double our height, we get double the gravitational, potential energy. Now, if I say I had a constant height and I had a constant mass, but my planet was changed, I would get E directly proportional to G. So if I double my gravitational field strength, so if I go to a planet twice the size of the Earth, ish, right? That's not a real direct figure. I would get twice the gravitational potential energy. And so again, you can kind of see the pattern now. If I had a constant gravitational field strength, so I was on the same planet, and I had a constant height, I could get GP directly mass. So if I was to double my mass on a planet at a constant height, I would get double my gravitational potential energy. And you can see that all three of these are directly proportional relationships. Okay, so now let's have a look at a worked example. As always, we're going to go through and we're going to highlight all of our keywords. So, the figure below shows a student before and after a bungee jump. The bungee jump has a bungee cord has an unstretched length of 20 meters. The mass of the student is 50 kilos. The gravitational field strength is 9.8 newtons per kilogram. Write down the equation which links gravitational field strength, gravitational potential energy, height, and mass. Okay, so that's just our GPE equation. So that's GPE, gravitational potential energy, rather E GPE, equal to mgh. Okay, so that's our first part right there. Now, calculate the change in gravitational potential energy from the position where the student jumps to the point 20 meters below. Okay, so we can see that the position that the student is at before can be called zero position. Okay, so we can call this 0 meters. So if they're jumping 20 meters below 0 meters, they've just moved through a height difference of 20 meters. So all we do is substitute all of our numbers into the GPE equation. Let's do that over here. So GPE, EG, I should say. Now, as always, this is joules, this is in G is in and H is in meters. Thankfully, we don't have to do any conversions. All of our units are already in their standard forms. So all we do is multiply them together. So mass of the student, 50 kilos, multiplied by gravitational field strength, which is 9.8, multiplied by the height difference. That gives us 9,810 joules. Now, you might think that that's the final answer. Well, all of our numbers in our data are given to two significant figures. So we also give our final answer to two significant figures, that being 9,800 joules.